We're going to move into um, electricity unit this today. Just a quick distinction. Normally, we would talk about static electricity and current electricity, and they're two different things. Static electricity deals with stationary charges that only flow briefly as it charges or discharges. Lightning in the picture here is an example. Also, if you walk across the carpeting and you get a shock when you touch a doorknob, that's static electricity. Current electricity deals with a constant flow of charge. Current electricity required the development of a constant pump of charge to make that work. Uh, Before we get into that pump, just a quick reminder, a couple things about the atom. Uh, Remember, electrons are negatively charged, protons are positively charged, but it's only the electrons that really can be moved around in a circuit. We can't move protons around unless we involve a nuclear reaction, which typically you don't have in most households or classrooms. A couple other quick reminders, probably the most important one: charge is never created or destroyed. It simply moves from one place to another. For example, if you rub a balloon on your hair, the balloon has a greater affinity for electrons than your hair does. And so it will steal electrons from your hair. The balloon becomes negative because it gains electrons. What charge does your hair end up with? It ends up being positively charged because it lost negative charge. It lost electrons. The smallest amount of charge is the charge on an electron, which is negative, which is equal on the opposite side to the proton, which is positive. Because we usually deal with a large number of electrons, we usually don't count individual charges or electrons, but work with large group of charges, just like you did work with moles in chemistry instead of working with individual atoms or molecules. What is that unit? Well, the SI unit, or the metric unit for measuring the magnitude of charge, is the coulomb. 1 coulomb is 6.25 times 10 to the 18th fundamental charges. Um, each individual charge, either E minus or P plus, oftentimes just written as E. The idea here is coulomb is to charge what the mole is to mass in chemistry. In a lot of ways, this number right here, which I don't want you to memorize, is sort of like Avogadro's number for charge. Remember Avogadro's number? 1 mole was this many atoms or molecules. 1 coulomb is this many fundamental charges, or this many of these. Um, what does that mean? So this gets a little interesting. If this many charges make up 1 coulomb, what's the charge on one electron? Well, one electron is one part of that many coulombs, and so the charge on one electron is 1.6 times 10 to the negative 19th coulombs. And that's a number that's worth memorizing. The charge on an electron, negative 1.6 times 10 to the negative 19th coulombs. The charge on a proton, positive 1.6 times 10 to the negative 19th coulombs. So now some definitions. And these you may have heard before, but may have never seen the actual definitions. So current, we're going to talk about in just a second, electrical current, is equal to the rate of flow of charge in coulombs per second. Now, a couple quick notes. Charge, we've been talking about it. The variable we use for charge is Q. And we just talked about it's measured in coulombs, that's our unit, which can be abbreviated capital C. Electric current is represented by the variable capital I, and it's measured in coulombs per second, or because we use it so frequently in everyday life, it's given its own unit, the ampere, which can be abbreviated either amp or just plain A. And here's the equation for electrical current. Electrical current is the rate of flow of charge, technically delta Q over delta T. It's how many coulombs of charge pass a point each second. And then finally, electrical potential, which in common parlance is often just called voltage, is represented by a variable V. It's defined as the amount of work done per unit charge. It's measured, since work is in joules and charge is in coulombs, as joules per coulomb, but again, because it's used so commonly in everyday life, it's given its own unit as well, the volt, which unfortunately gets abbreviated V. So here's the equation for electrical potential. And I just want to mention one thing here very quickly. There's an unfortunate thing that happened with electrical potential. Let me quick explain. The variable for electrical potential is capital V, and so you could have something that looks like this. You could say the electrical potential in this particular battery is 12 volts. Well, here's the unfortunate happenstance. Variables are always bold, but if you remember, voltage, the unit for electrical potential, can be abbreviated with just a V. So here's the unfortunate part. The variable for electrical potential and the abbreviation for the unit of electrical potential is the exact same letter. The only difference is variables are typically bold and abbreviations are italicized, but oftentimes you don't see it. Don't let this confuse you. Electrical current. Just real quick note, Ben Franklin was one of the first experimenters with electricity, and he actually thought, this is long before electrons were discovered, that it was positive charge that flowed around the circuit. He thought the positive end of a charged object had an excess of positive charge, and the negative end had a deficit of positive charge. So he thought that positive charge flowed around the circuit from the positively charged object to the negative pole of the battery, which was missing that positive charge. That's the direction that we define as current. So we say that current actually goes around the circuit from the positive end of the battery to the negative end. It's called conventional current, which actually in this case means old-fashioned current, a la Ben Franklin current. In reality, though, what's really happening in electrical circuits, electrons are actually moving from the negative terminal of the battery around the circuit this way to the positive terminal, which has a deficit in electrons. Electrons weren't discovered to the 1890s. By then, it was simply too late to change all the 100 years of books that were in all the libraries. And so even today, we still use conventional current. What does it mean? The magnitude's still the same, the number of coulombs per second, but the direction's just not the direction the electrons are moving. Don't let that stress you out, but I just want to give you a little bit of history. Real quick practice, the current in a light bulb is 0.35 amps or 0.835 coulombs per second. How long does it take a total charge of 1.67 coulombs to pass through the filament? And you're like, whoa, wait a second, what's going on? Well, remember the definition for electric current. And now it's just plug and chug. I represents the electric current, Q represents the charge, T represents time. Plugging it in, the current, I, is that many amps. The charge is 1.67 coulombs, and we're just trying to solve for time. Doing your algebra, you should discover it's about 2 seconds. One more example, I'd like you to try this one on your own. So pause the video if you're watching. Total charge of 1.8 coulombs passes through the film in the bulb in 0.85 seconds. What's the current for this light bulb? Pause now if you'd like. All right, solving this one, just using our equation again, plugging in what we know. In this case, we know the charge, we know the time, and so we very quickly can calculate the current for the light bulb, about 2.12 amps. Batteries. The word battery actually comes from the military or means a group of cannons. In physics, it refers to a group of electrochemical cells. Here's the big idea. Batteries do work on charge. They do not create or store charge. The analogy is they're exactly like water pumps. Water pumps don't make water. They just do work on water. They increase the pressure of the water that passes through them. The exact same thing is true for batteries. They increase the potential. It turns out that's exactly equal to pressure. It increases the pressure of the electrons that pass through it. A 1.5 volt cell does 1.5 joules of work on every 1 coulomb of charges that passes through it. Most of you are familiar with 1.5 volt batteries. They look like this. Current normally goes from negative to positive. As the charge passes through that conventional current, it does 1.5 1.5 joules of work on every 1 coulomb. If you send 2 coulombs of charge through here, it does a total of 3 joules of work. If you sent 4 coulombs through here, it would do a total of 6 joules of work. A 9-volt battery, this is one of those, you may not be as familiar with these, do 9 joules of work on every 1 coulomb of charge that passes through it. It's that simple. In this case, let's see here, it's a negative terminal, positive terminal. It does work as it passes from here to here. Again, this is conventional current in both of these cases. How was the battery discovered? It was actually Luigi Galvani's wife. She was actually preparing frog legs to make soup that night and was using a copper fork and an iron knife or steel knife. When she was trying to clean off the excess fat from the frog leg, she discovered that whenever she held both of those and touched it, even though the frog leg was disconnected from the frog leg would actually jump. Galvani, this is an illustration from his book showing the same thing, discovered you didn't have to use a copper fork and a steel knife. You could just take a piece of copper and a piece of iron connected here and the frog leg would jump. And he tried bunches of different experiments. You can see him down here, and here he's doing it with a sheep, discovering it doesn't just work for frogs, it works for all animals. And yes, it led Mary Shelley to eventually write the book Frankenstein, where they reanimate dead body parts by using electricity. The idea that somebody can make it alive. In reality, no, it doesn't make it alive again. It's just that our muscles are all activated by electricity. And he had accidentally stumbled upon the first battery. How do you make a battery? The answer is all you need is 2 dissimilar metals. If you've got a group of cells, you can actually produce a battery. A battery is a group of cells. If I hand you a piece of copper and a piece of zinc and have you hold it in your hand, you are actually a battery. You can actually run an LED or a small watch off of the electricity produced by that. You're like, wait, are we stealing body electricity? The answer is no. You can actually just replace the person with a potato or salt water or lemon. The key here is the 2 dissimilar metals. In this case, a zinc-coated thing there and a piece of copper here is still going to run your LED over there. How does it work? Well, every metal, if you remember back from chemistry, has a different affinity for electrons. If you put 2 metals in a solution, one of them is going to have a greater affinity for electrons and is going to steal electrons from the other metal. And that's how you make a battery. The one that steals electrons is going to become negatively charged. The metal that lost electrons is going to be positively charged. And so, yeah, you can just make a battery that way. Oops. I've got things here. Real quick note on this one. What batteries do we currently use? We use lithium-ion batteries, where we use lithium over on this side, and which doesn't mind losing electrons, and hydrogen ions, which if you charge them, you can actually move them over on this side, which have great affinities. And so you can actually produce really decent batteries. All of our batteries powering your laptops and your cell phones right now are lithium-ion batteries. This gets a little tricky. I need you to think about this. So batteries act a lot like pumps. So in this case, each one of these batteries over here hooked in series, that means one after another, is going to try to do 1.5 joules of work on each coulomb that passes through it. So each one of these batteries, 1.5 volts. Now what the question is what happens if you put them one after another? So the charge is going to go for this first one, then go down this way, and then go into this one, then go down this way, and then go into the next one. This device over here is called a voltmeter. It measures volts or electrical potential. And my question is what is this device going to read in this case? Well, think about it for a brief moment. You can even pause and talk to your neighbor if you'd like. What is it going to read? It's going to read a total of 4.5 volts. Why? Charge goes through this first one, gains 1.5 joules in every coulomb. Then it goes through this one, gains an additional 1.5 joules for each coulomb. Then goes through this one and gains another additional 1.5 joules per coulomb, giving us that. Now, what happens if you put them in parallel? Well, in this case, all of them are trying to pump. And you might say, oh, it's the exact same result. We're going to get the same thing. But I need to mention something real quick. Charge can only either go for this battery or this battery or this battery and before it comes back out here and goes for the voltmeter. It can only go through one of these. And that may be enough of a hint for you to figure out the answer on this one. What is this voltmeter going to read? The answer is it just reads 1.5 volts. Why? The charge either goes through this one and gains 1.5 joules per coulomb, or this one, but it doesn't go for all three of them. What's the analogy here? The analogy here is each one of these are acting one after another. I told you batteries are a lot like water pumps. What's happening here? It goes through the first battery, that's like the first pump, comes out of there with higher pressure, goes into the next pump, which increases the pressure even more, goes in the next pump, increases the pressure even more. It increases the pressure or voltage, but not the maximum flow rate. If there's 1 liter per second going in here, 1 liter per second comes out there. Batteries in parallel? What's happening here? It's like having pumps side by side. In this case, if each one of these could handle 1 liter per second, the flow rate now is increased. Now there'd be 3 liters per second going into this thing and 3 liters per second coming out, but it would only have the pressure of one of the pumps. So it increases the maximum flow rate, but not the pressure. That's exactly what's happening here. Why would you ever put batteries in parallel? It increases the flow rate, the current, which we'll talk about in a second. If you needed to drive something that required a lot of current, you put batteries in parallel. Tesla does this with their cars. Their batteries are both in series and parallel, but why are they in parallel in the car? To increase the maximum current that can be supplied to the motors. Brain break, if you want to try this one real quick. 2 correct answers for each clue. The answers saying the same letters and blanks. At this point, if you want to, pause it and then come back. Here are the answers. There's probably other ones as well. But yeah, hopefully you got a few of these. All right. This chapter deals with direct current, DC. But the plugs in this room and your home are all AC. Whoops, I forgot to change this slide. In the U.S., we use AC in the household. Alternating current means that the current flows back and forth, not just in one direction. And in the US, that's at 60 hertz, 60 oscillations per second, which means the electrons jiggle back and forth 60 times per second. There's advantages to alternating current. You can use a device called a transformer, but all of our small devices use direct current. Your computer, your phone are all direct current. We have devices, your transformers that you plug in, power supplies, convert AC to DC to run those devices. In this chapter, though, we're only going to focus on direct current. One other part we've got to mention real quick is batteries do work on charge. They increase the energy of the charge. But charge always loses this added energy as it flows through the circuit and back to the battery. Circuit literally means circle. All electrical circuits are basically circles. All circuits, except for superconducting circuits, offer some resistance to the flow of charge. Resistance is measured with the variable V, and it's measured in ohms. Now, ohms should be abbreviated capital O, but that would be confusing if you put it with a number. So we use omega as the abbreviation for ohms, the unit of resistance. The resistance depends on the length of the material, the area, and something called the resistivity. Resistivity is represented by the Greek letter rho, and we'll talk more about that. Each material has its own unique resistivity. The analogy here is if you've got multiple lanes in a rush hour traffic, there's less resistance to the flow of traffic. The same thing here is true. If you can increase the area through which water could flow, for example, let's say I'm trying to empty a water tank. Here's my water. Having multiple pipes would allow the water to flow out of the tank much more rapidly. It's harder to do a traffic analogy here, but imagine I hooked up that same water tank filled with water to just one pipe and then connected that pipe one after another. Well, each one of these would oppose the flow of water slightly, and so we get more resistance to flow if we make this pipe longer. That's the big idea on this one. Take a quick look at this. So here's a nice graphical representation. Here are things which have least resistance and more resistance, or greater resistance. If you make the same size wire longer, it has a greater resistance or greater opposition to the flow of charge. If you make the same length have a greater cross-sectional area, its resistance becomes less than the one that has a smaller area. Copper is a better conductor than aluminum, so copper has less resistance given the same size or area and length as aluminum would. And then finally, temperature. For metals, as you warm them up, their resistance tends to increase. Now, for semiconductors, that's the exact opposite. Semiconductors like silicon, germanium, as you warm them up, actually become better conductors. So take a look here. I just want to show you a table of resistivities. So rho here is resistivity, the thing I was talking about. And if you look on here, the best three conductors are copper, silver, and gold. If you look at their resistivities over here, which one of these three is actually the best conductor? Which has the lowest resistivity? The answer is, believe it or not, silver. You're like, wait, why don't we use silver then? Well, A, it's kind of expensive, and B, it tends to tarnish. What's the next best conductor in this table? The answer is copper, which we use in all of our household wiring. But one of the questions I have for you is, why do we use gold then for electrical connectors in computers and on headphone jacks? It's actually not the best conductor. Why don't we use copper plating or silver plating? And the answer is actually more chemistry than anything else. Both copper and silver oxidize and tarnish, whereas gold does not. So out of the three best conductors, why do we plate computer connectors and headphone jacks with gold? They do not change. And so it's probably the best conductor that doesn't oxidize. Take a look at this quick checkpoint. This one's a little tricky. Which one of these three things, they're all copper, has the greatest resistance and the smallest resistance? Pause if you would like at this point. Here's the answer. If you look at it, B has one of the smallest cross-sectional areas, and it has the greatest length. So which one of these three has the greatest resistance? Well, it's definitely B. B is the greatest, but now comparing A and C, which one of A or C is the largest resistance? We're like, well, obviously C, because it has half the cross-sectional area, and if you plug it in up here, it's going to have, because this is smaller, it's going to have a greater resistance. But there's a trick to this one. The length is always half as large as well, which means this also gets half as large. This gets twice as big. How does the resistance of A and C compare? The answer is they're actually the same. A trick question. All right. Quick example one. I want to show you one, just quick practice one. A 1 millimeter diameter copper wire is 100 meters long. What's its resistance if the resistivity of copper is that? Remember, cross-sectional area for a circle is pi r squared. And so in this case, the area down here at the bottom becomes pi times the radius squared. So the 1 millimeter diameter, this is half a millimeter converted to meters. And you'll discover its resistance about 2.19 ohms. Another brain break. I'll let you pause if you want before I show it. These are all names of countries in Europe. Actually, one of them is no longer a country. See if you can figure this one out. And when you're finished, the shaded spells out the capital of one of these. Here's the answer: Warsaw, the capital of Poland. I'm not sure if Serbia is still a country. I think it actually may be. All right. So quick review before we get going here. There's some nice analogies between electricity and plumbing. Electricity, we've got charge measured in coulombs. That's exactly equivalent to a plumbing concept, but usually plumbers measure volume, at least city organizers, measure volume in cubic meters of water. Current is the same in both of these, except now here we deal with coulombs per second, here we deal with cubic meters per second. Potential is exactly equivalent to pressure. Pressure is measured in newtons per meter squared or pascals. Potential joules per electrical potential joules per coulomb or volts. And then finally, we talked about resistance. And unfortunately, there's not an exact equivalent in plumbing, but plumbers or city designers will talk about the flow resistance, and they try to minimize that to make sure everybody gets enough water. Schematics. We usually don't draw circuits with actual pictures of batteries and light bulbs. So a schematic diagram is a shortcut to sort of draw these. And a wire is just drawn as a line, doesn't matter how long it is. A resistor, we'll talk about what that means, or current load looks like this. A light bulb usually looks like this, sometimes drawn with a curly Q on the inside instead of that. A plug looks like that. A battery looks like this. One long line, one small line. This represents the two dissimilar metals, so you can sort of see it. The long line is always the positive terminal battery. A switch looks like this, and a capacitor, which we won't talk about, looks like this. So down here, here's a typical example. This is a battery, a couple of electrical cells. This would be the positive terminal over here. Here's a switch, and here's a light bulb, which is our load. And the wires here are the path that it takes. Real quick note on this one. So here's the schematic diagram. Which direction does current flow in the circuit? The answer is, you should have guessed, oh yeah, we use conventional current, so it flows from the positive towards the negative. And so it would go counterclockwise around this circuit. And here's the symbol for a resistor. Here's the symbol for a battery. One quick note on this one, you can actually measure the magnitude of the current using something called Ohm's law, which we'll look at in just a moment. And then I want to mention this just real quick. In Commonwealth countries, they draw the schematic for a resistor like this. Don't let that bother you too much. It's just another way of drawing it. I just want to say, you may see it sometime in your life, and I just wanted to mention it to it. Schematics are pretty uniform everywhere except for this term, and again, the symbol for a light bulb varies slightly. But yeah, just a quick note on that one. The software I use to draw my circuit diagrams is actually from the UK, so you'll see my resistors this way. Don't let that bother you. It's the same. All right. So quick review before we get going. Potential, variable, electrical potential, variable is V, is the electrical equivalent of pressure measured in volts. Electrical current, represented by the variable I, is the electrical equivalent of flow measured in amps. Resistance, variable R, is the opposition of the flow of charge measured in ohms. And here's my quick check question. Does a voltage or pressure always create a flow of charge? I'll pause for a second and then give you the answer. Almost every single student says, of course, yeah. But think about it. There can be water pressure in the pipe behind a faucet. Does that mean that there's a flow of water? Well, the answer is no, not unless the faucet's turned on. Likewise, with a battery, unless there's a circuit, in other words, a connection, say, for example, to a light bulb, that allows for the flow of charge, a battery by itself won't actually have a flow of charge. So the correct answer on this one is, believe it or not, no. They're not necessarily a flow of charge. Ohm's law. This is George Simon Ohm came up with this very simple relationship. He said the current in the circuit is directly related to the voltage divided by the resistance. And as long as we measure resistance in the right units of ohms, this works out really nice. One of my students gave me this picture once. They're like, this makes sense to me. Voltage is the pressure. It's the thing trying to force the charge around the circuit. The charge or the current is actually the amp. And resistance is trying to oppose the flow. It tries to tighten down the pipe. They're like, once I saw this picture, it all made sense. Okay, so they said, you got to show all the other students. So I always do now, for those of you who need a visual representation of this. Quick practice problem. Here's Ohm's law up and top, written very simply. Current is equal to voltage over resistance. The resistance of an iron is 19 ohms. What's the current in the iron when it's connected across a potential difference of 120 volts? 120 volts is the standard electrical potential of the plugs in our homes. Trying this one real quick, just using Ohm's law, plugging in what we know. Voltage is 120, resistance 19 ohms. You'll get the current of about 6.32 amps. So here's a quick one. All of these light bulbs, and I went back to drawing pictorial ones in this case, have the exact same resistance. They're all identical. The question is which one of these circuits is going to have the brightest light bulb? Or in other words, is going to have the greatest current going through the light bulb. All of these batteries are capable of fully running the light bulb. So the question is, write the brightness or the current through the light bulb from greatest to lowest. And a lot of students say, it's easy. C greater than B greater than A. Because, C has 3 batteries. But again, they're hooked up in parallel, which means the potential in all of these cases is just 1.5 volts. So what is the correct answer on this one? It's a trick question. The correct answer is A equals B is equal to C. They all have the exact same voltage, all the same resistance. And so, yeah, the current is actually identical. Here's a slightly more exciting one. Now, just real quick on this, I'm going to draw the direction that the batteries are pumping charge, just so you can sort of visualize this one. My question is this time, which one has the greatest current? Which one has the least? And I'm going to pause for a second here because I need you to look at these and be careful. I'll give you a hint on that one, a hint on this one, and then this one is a little tricky. All right, I'll pause for a second before we talk about it. What's the ranking on this? Well, the voltage generated by these 2 batteries is 3 volts because one does 1.5 joules of work on each coulomb. This one does another additional 1.5. The same thing is true with this one. And again, all of these light bulbs are identical, all have the same resistance. We're just using Ohm's law. Which one of these is going to have the greatest current? Well, it just depends in this case then on which is the greatest voltage. In this case, there's 1.5 volts running this light bulb. And then the tricky one, this one here, this pump is trying to pump it this way, clockwise around the circuit. This one's trying to pump it counterclockwise. What's the net voltage on this one? What would happen if you had 2 pumps trying to pump things in opposite directions? The answer is this one's 0 volts. And so what's the correct ordering on this one? B is equal to C. Both of them have 3 volts, which is greater than A, which is greater than C. So it's kind of a trick question. So quick using Ohm's law here. We've got a voltage on a battery and this. First of all, what's the current in this circuit? Well, if you plug it in 1.5 volts over 0.5 ohms, you should discover your current is going to be 3 amps. Which way is it flowing? We're going to use conventional current, which means we're going to assume current comes out of the positive end of the battery. And so, whoops, wrong direction. You should discover in this case, there should be 3 amps of current going around this circuit in this direction. All right. Here it is with schematics. This time a little bit more interesting. We've got a resistor, or a device which has a 7 ohm resistance. We've got 3 amps of current going through the circuit. The question in this case is, what's the electrical potential or the voltage of this battery? How do we solve this one? Again, a plug and chug problem. In this case, though, we know the current is 3. So using the equation here, we're looking for the voltage. And we know the resistance, R, is 7. And most of you can very quickly figure this one out. What's the voltage in this circuit? electrical potential has to be 21 volts. Again, slightly confusing. Maybe I should write out the units to avoid confusion. 21 volts. All right. What happens if you, what about this circuit? So now I'm doing schematics. Again, take a look at it. We've got two batteries both trying to pump charge in the same direction. This time they're not 1.5 volt batteries. They're a 10 volt battery and a 6 volt battery. What do we do in this case? We simply need to add the voltages together. So these together act like a single 16 volt EMF source. What's that going to be, or what's that going to do to the current in the circuit? Well, now just plugging in our numbers, I equals V over R. We get 16 over 2, so the current in this circuit is going to be 8 amps. So there'll be 8 amps of current flowing through this. Now, at this point, I want to ask you a tough question. What's the current at this part of the circuit? Or what's the current at this part of the circuit? The answer is, in each one of these cases, because charge can't be created or destroyed, there's 8 coulombs of charge per second flowing through the resistor. That means there has to be 8 coulombs of charge flowing from the batteries this way, and there has to be 8 coulombs of charge flowing back to the batteries. Charge is not destroyed. We don't destroy any of our electrons. And because it's got to be conserved, any amount of charge that comes out of this battery has to be coming into it. Remember, the batteries don't create charge. At every single point, the current is going to be 8 ohms, or 8 amps, sorry. What about this one? I'm going to pause for a second before I answer this one. We've got 2 batteries, but this time the resistor is placed between them. Both of these are trying to force charge around the circuit counterclockwise. I'll pause for a second, let you guess on this one. What's the current in this circuit? Both these batteries are trying to pump charge around the same direction. It's still going to be 16 volts of total electrical potential. The current in this circuit is still going to be 8 amps, which is the same everywhere throughout this circuit. What about this one? Now, this one, be careful. Like, wait, you just showed us this problem. Well, this one is a little bit different. This battery is trying to force charge this way. This one's trying to force charge this way. You're like, oh, zero. It's like the 2 batteries going against each other. Yeah, except one of these is a stronger pump. The 10 volt battery is a little bit larger. How do we solve this one? You may have guessed already. If you haven't figured it out, in this case, we don't add the voltages or electrical potentials due to each battery. We're going to subtract them. And so what's the current in this circuit? The answer is it's going to be 2 amps. Which direction? The 10 volt battery is going to win, and it's going to force charge around our current around this thing, this direction. What's going to happen to our 6 volt battery? It's actually going to get charged. It's going to have charge forced into it. And so it's going to charge while our 10 volt battery is going to discharge. Electrical power. Take a quick look at this. I wrote this out in words. Electrical current, I, is charge per unit time, and electrical potential is energy per charge. What do you get if you multiply these two by each other? Watch real quick. I'm going to write it this way as well. You end up with this. Charge cancels, and you get work per time, which is electrical power. So current times voltage gives you electrical power. Power, remember, is how many joules per second something's producing or using. And if you use Ohm's law, you could replace the I in this circuit here with V over R. And so you could also write electrical power as V squared over R. Or you could replace voltage by rearranging this as I times R. And if you do that with the original equation, you'll get I squared R for this one. So here's the possible equations for electrical power. Which one's the most convenient? The answer is depends on what you know. If you know current and voltage, first one, voltage and resistance, second one, current and resistance, the last one. Every single device you see around this room has a power rating. If you go to your Mac or whatever your iPad probably can't do it, but if you go to like a laptop, you can actually go and find out what the wattage of this thing is. In this case, this is on my computer, it's a 60-watt charger, and you could very quickly figure it out if you plugged it into a socket. Sorry, I used 220 volts, but you could use 110, just different answer. You can also use this to actually figure out power dissipated. Remember, batteries do work on charge. What happens when that charge passes through a resistance or a load? It loses that energy. What form does that energy become? It becomes E-dis, or thermal energy. The resistor gets warm. Oh, by the way, a resistor is just a device which is designed to have resistance. So in this case, we know voltage and resistance. So probably use this equation for power, and you'll discover that this thing is going to radiate 128 joules of heat energy every second, or 128 watts. It is a pretty decent heater. Every month, your parents get a bill for the amount of electricity that you use. And it's billed in a really weird unit. It's measured in kilowatt hours, and you can see it here on this meter. My question is kilowatt hours a unit of energy or a unit of power? Pause for a second, think about it, and then I'll show you. If you remember power is energy over time, you can rearrange that as power times time is equal to energy. Kilowatt is a unit of power. It's 1,000 watts. Hour is a unit of energy. So a kilowatt hour is a form of energy. 1 kilowatt hour is 3,600,000 joules of energy. And yeah, you get billed in groups of that each month. Oh, another brain break. Pause if you'd like. Answers are this. Matthew, Mark, Luke, and John. Spring, summer, spade, summer. Oh, wow. Triple or Homer. Oh, I would have missed that one. Earth, fire, and air. Okay, anyway. So in this case now, we can actually look at it in a couple of different ways. What's the current through the resistor, in this case the bulb? What's the voltage drop? And what's the power? In this case, you should be able to figure out very quickly just using Ohm's law. The current in the circuit is going to be 1.5 amps. And the power we could very quickly calculate. I would do probably V squared over R. So in this case, 1.5 squared over 1 should be about 2.25 watts, if I'm doing my math right. Oops, forgot my unit. But then voltage drop, we've never talked about yet. But I just want to give you a quick hint. Normally we put the 0 point by the negative terminal of the battery. The battery increases the electrical potential by its rated amount, 1.5 volts. And what happens after it passes through the load? Well, it actually goes back down to 0 volts, all the way back around the circuit. And we'll talk a little bit more about that in just a second. So how much did the voltage drop? Well, it was 1.5 volts just before it went into the light bulb. It was 0 volts after it went through the light bulb. So the change in voltage here would be 1.5 volts. And so you can solve it. All right. If you have resistors one after another, it's called resistors in series. How do you figure out the total resistance of the circuit if you've got those? Well, logically, you might have guessed already. You simply add them together. And the current going for each resistor in series is always the same. In the circuit shown below here, what's the total resistance of these two resistors together? Well, just 2 plus 4 ohms, or a total of 6 ohms. What's the current going to be in the circuit? Well, if we use Ohm's law, V over R, 12 over 6, the current in the circuit is going to be 2 amps. And so the current flowing through each one of these resistors is going to be 2 amps as well. Sorry I didn't label it with I this time, but you get the idea. 2 amps going for each one of these, and still 2 amps flowing back to the battery. Take a quick look at this circuit. I want you to practice one real quick. Find the total resistance of the circuit, called the equivalent resistance, and the current in this circuit. And this is a 9-volt battery shown below. Give it a quick try. Here's the answers. Total resistance is the sum of all of those, in this case all of these. So the total resistance is 18 ohms. Using now Ohm's law, current is equal voltage over resistance, we can calculate the current in this circuit is 0.5 amps, which means 0.5 amps is leaving the battery, and at every single point in the circuit, each one of these devices has that much current passing through it. Again, we cannot create or destroy charge. What we do use up is the electrical potential of the charge, but we don't destroy any of the charge as it goes around the circuit. Batteries don't make charge, they just do work on charge. You might be familiar with Christmas tree bulbs. In Christmas tree bulbs, all of the bulbs are like resistors, and they're all hooked up in series. The problem with these is if one of the bulbs burn out, like the one shown here, now there's no longer a path for it to flow. It's like that closed spigot. There's no way for charge to flow from one terminal to the other. What happens? All the light bulbs go out, which is why if you've got one of these old strands, if one of them burned out, the whole strand would go out. Nowadays with LED Christmas tree bulbs, it's not nearly as a problem. LEDs last so long that it's usually not a big deal. Voltage drops. I mentioned it in that first slide, but I just want to get into it very quickly here. If you take Ohm's law and rearrange it, multiply both sides by resistance, you can actually calculate how much voltage change you have across the resistor. In this case, you can calculate the voltage drop is equal to I times R. Here's the circuit we looked at a moment ago. We know there's 2 amps flowing out of the battery, 2 amps going through each one of these resistors. What's the voltage drop across the circuit? I actually want to show it to you real quick so you can sort of visualize it. The voltage drop across these is just going to be equal to I times R. So the voltage drop across this one is going to be equal to 2 times 2, or 4 volts. And the voltage drop or potential drop across this one, I could probably do without writing the whole thing out, is going to be 8 volts. So what in the world's happening in this circuit? Well, remember, here's our battery, and we usually make the negative end of the battery 0 volts. I'm going to write it over here at the corner. So by the time it goes through the battery, it gains 12 volts of potential. It's still 12 volts here, but now when it flows through this resistor, it's going to lose 4 volts of potential. So what is it at this point in the circuit? The potential at this point in the circuit is now 8 volts. And then after it flows through this resistor, it loses an additional 8 volts of potential. Oh, hey, look, it's back down to 0, which makes sense. It's lost all the potential that the battery gave it. So before we go on, take a look at this circuit. So here's Ohm's law and the voltage drop equation. What are the voltage drops around this circuit? And now one quick note on this one. I need to connect a line here real quick. This symbol, if you ever see an electrical circuit, it means that that point in the circuit is connected to the earth, literally to the ground, and it's called the ground. And we assume that the electrical potential of our planet, the earth, is always at 0 volts. That means that point in the circuit, by definition, will be 0 volts, which means now we can say that this end over here is definitely at 12 volts. So in this case, if you ever see that, that point of circuit has to be 0. It turns out you can actually put the 0 point anywhere you want, but this makes it more obvious in a circuit. But before we can answer the voltage drops, we need to figure out the current in the circuit. First of all, what is the total resistance of the circuit? Well, these 3 resistors are in series, so our total, the total resistance of all these together, is going to be 1 plus 2 plus 3, which is going to be 6 ohms. What's the current flowing out of the battery? Well, if we use Ohm's law, V over R, we've got a 12-volt battery, and the equivalent resistance of all of this is 6 ohms. So there's going to be 2 amps flowing out of the battery. And so here's our battery. It's going to be 2 amps flowing out. And I'm just going to draw the 2 amps on each one of these resistors. We can now figure out the voltage drops across each one of these. And I'm just going to do it sequentially. The voltage drop across this top resistor is going to be 2 times 1 or 2 volts. I was at 12 volts before I went through this resistor. What am I going to be after I go through it? The answer is 10 volts. I've lost 2 volts of potential. The voltage drop across this resistor is 2 volts. Voltage drop across this one is going to be 4 volts, 2 times 2, I times R. And so what am I going to be at this point? Actually, I probably should write this out. The voltage drop in this case then for this resistor is going to be 4 volts. I was at 10 volts. What am I going to be after I go through this resistor? The answer is 6 volts at this point in the circuit. Actually, this whole range of wires at 6 volts. And then the voltage drop across this one is going to be 6 volts. What am I at again after I go through this one? Oh, hey, back to 0 volts. Yeah, it always works out. What if you put the potential somewhere else? What if I don't have it, and let's say they put the ground here? This gets a little weird. Don't freak out, but I want to quickly walk you through it. This circuit's exactly the same as before. Current's still flowing around the circuit this way. 2 amps for each one of these. And the voltage drops are still the same. But we've got a weird problem here. And don't let it bother you. The voltage drop across this bottom resistor, I'm going to work clockwise around this thing again, is 6 volts. What am I going to be then at this other bottom corner if I lose 6 volts and I start out at 0 volts here? Well, the answer is I'd be at negative 6 volts of potential. Don't let that bother you. It's okay. The battery is going to allow me to gain 12 volts of potential. What am I going to be here? The answer is 6 volts. Voltage drop across this one is 2 volts, which would put me over here at 4 volts. And then the voltage drop across this one, 2 times 2 is 4. Hey, it works again. Yeah, it turns out no matter where you put the 0 point, it'll always work out. But if you see a ground statement, always make that the 0 point. One last note on this one, and I'll just mention it real quick. As batteries go dead, they have what's called an internal resistance. It's almost as if there's a resistor inside of it. What's the resistance from? It's actually from salt buildups on the metal electrodes that make up the battery. The electrolyte will react with the metals and make, for example, zinc hydroxide and copper chloride in a regular battery. And those salts, the zinc oxide, copper oxide or zinc chloride, have a low conductivity. They're salts, and so they act like an internal resistance, R. Why do batteries go dead? The current in the circuit gets smaller and smaller as the internal resistance builds up. So in this case, the current in the circuit now would be smaller than before. It's still a 1.5 volt battery, but now the resistance of our circuit is actually 1 plus 0.1 due to that internal resistance. And so the current in the circuit gets smaller, which means my light bulb gets dimmer. Another brain break. Pause if you'd like. A lot of them today. Here's the answers. You can very quickly, we've actually solved this one already. We've done the voltage drops across this one, so I'm going to skip this one. And take a look at this one as well. So take a look at this. The total resistance of the circuit, the sum of these three would be 9 ohms. And so the current coming out of the battery is going to be 4 amps. And so I just want to quickly do this one with you. There'll be 4 amps going through each one of these. And you can very quickly calculate the voltage drops across each one. And if we do this, and I'm going to do a little bit faster this time than we did before, I'm going to put the 0 point here, 0 volts. I end up at 36 volts here. And now we got to do a little bit of math. Don't worry. 36 volts coming into this first resistor. Voltage drop here, 4 times 2 is 8. If we subtract 8 from there, it will be 28 volts at this point. Voltage drop across this one, 4 times 4 is 16. 28 minus 16 is 12 volts. And then finally, the voltage drop across this one, 3 times 4 is 12. Hey, look at that. Yeah, it always works. Last thing I want to get into today is what happens when resistors are side by side, in other words, parallel. We know the resistance of this top part here is 9 ohms, but what in the world is the resistance of this thing? And the answer is you've got to work a little bit harder on this one. But let me show you the mathematics on it. For resistors in series, you simply add them together. That's what we've been doing up to this point. For resistors in parallel, it gets a little trickier. You have to take 1 over each resistance, and then that together gives you 1 over the total. So let me show you here real quick. 1 over the total resistance in this case would be equal to 1 over 3, the first resistance, plus 1 over 6. Careful, how do you add fractions? You've got to find common denominators. So this, if you do it, becomes 3/6. So what's the total resistance of this thing? It ends up being 6 over 3, or 2 ohms. So it actually has less resistance in either one of these. Why? It actually allows for an additional path for charge to flow. If it was just the 3 ohm resistance, or without the 6, it would be 3 ohms. But this allows the resistance to come a little bit less because it allows for another path for it to flow through. For resistors in series, the current for each one of these has to be the same. There's no way for it to change anywhere. What's true about resistors in parallel? Well, resistors in parallel, the voltage drop has to be the same. Whatever the voltage is here, say for example 12 volts, and let's say over here it's 6 volts, the voltage drop across each one of these has to be 6 volts. Delta V is going to be 6 volts if the charge goes through this one, or 6 volts if it goes through the bottom one. You can solve it. Parallel light bulbs, one nice thing, if parallel light bulbs, one of them burns out, doesn't matter. Current will still be the exact same for all the rest of them, and they'll all still remain the same brightness, assuming the potential is still the same on the plug, which is typically true. One example problem, and then I promise to finish with it. A 9-volt battery is connected to 4 light bulbs, each with different resistors, or 4 resistors as shown. Find the equivalent resistance of this circuit and the total current in the circuit. I'll pause for a second, let you try it. Here we go. Plugging in our numbers, we get this if you find a common denominator, which is really, oh shoot, this would be a 4 ohm, but I did the math right, I'm sure. Common denominator here is hideous. 140 is your common denominator, and so you get that. But our total then is the reciprocal of that, and is a decimal 0.92 ohms. What's the current flowing out of the battery? Well, we just plug it in, 9-volt battery over that total resistance. There'd be 9.8 amps flowing out of this battery down into the circuit, and then it would split up, and some of it would go for each of these bulbs. Last thing is summary here. You can quick see this. There's some nice analogies here. But yeah, at this point, you're ready for your worksheet. Good luck. Have fun with this, and we'll talk to you soon.